In this video, we're going to look at some properties of the integral that will facilitate computation. The first property is called additivity of domain. It says that if f is integrable on the interval ab and the interval bc, then f is integrable on the entire interval ac. Moreover, we can split the integral on ac into the integrals over ab and bc like so. Now this isn't surprising if we draw out what this looks like. We've got a function which we can integrate on the interval ac, and yeah, the integral on the whole interval is the sum of the integrals on each part. To see this in action, let's find the integral of a piecewise function on the interval 0, 2. While not necessary to the problem, let's graph this to see what f looks like. We see that the behavior of the function changes at the point x equals 1. So let's break this into the intervals 0, 1 and 1, 2. Applying additivity of domain, we can split our integral as so. Now the way we've broken this up lets us also split up the piecewise function into its pieces. At which point, we integrate each part separately by finding an antiderivative and applying the fundamental theorem of calculus. The next property is linearity of the integral. If f and g are both integrable on the interval ab, and c is a real number, then both f plus g and c times f are integrable on ab, and we can evaluate these integrals in the usual way, or at least a way that we want to be true. To demonstrate this property, let's integrate the function 3e to the x plus x cubed on negative 1, 1. Applying both of the linearity properties, we can split this integral across the plus sign and pull the 3 out from in front of the e to the x term. Computing each of these integrals separately, let's start with the x cubed integral. An antiderivative is x to the 4 over 4, and plugging everything in gives us 0. For the e to the x integral, an antiderivative of e to the x is just e to the x, giving us this as our answer. Putting it all together, the integral of 3e to the x plus x cubed is 3e to the 1 minus e to the negative 1. Now we're not going to use this last set of properties too much, but we'll introduce them anyway. This property is called monotonicity of the integral. If f and g are integrable on ab, and f of x is less than or equal to g of x for all x in ab, then the integral of f is less than or equal to the integral of g. This one's pretty easy to see with a graph. Let's draw two functions, with one bigger than the other. The blue area, corresponding to the smaller function f, is less than the green area corresponding to the bigger function g. So keep this one in mind, but we are not going to do an example of it. Finally, our last property is called subnormality. If f is integrable on ab, then the absolute value of f is also integrable. Moreover, the absolute value of the integral is at most the integral of the absolute value. We can see that the inequality is not an equality by looking at a specific example. Say f of x equals x cubed. Let me draw out both the functions x cubed and the absolute value of x cubed so that we can see why this is true. Remember that when we take the absolute value of a function, anything beneath the x-axis flips to being above the x-axis. Now the integral on the left is 0. We computed it previously in an example above. So the absolute value of this integral is also 0. To integrate the absolute value of x cubed, we're going to break it into the intervals negative 1 to 0 and 0 to 1. On negative 1 to 0, the function is negative x cubed, and on 0, 1, it's positive x cubed. After this, everything else is just algebra and finding antiderivatives, at which point we arrive at an answer of a half. If we put all of this together, we see that the inequality is strict since 0 is less than a half. We'll use these properties a fair amount in the future to help us compute integrals, so make sure that you study them and keep them in mind.